Okay, so today we are starting on a new topic. Primarily we are going to look at an alternative way of designing the control parts of the system, and the approach that we are going to follow is what is called microprogrammed control. Let us again look at the data control partition that we had considered before when we started the design using state machines. So there is a data part of the system and there is a control part of the system. These two interact with two sets of signals. One set of signal which originate from the control and go to the data are called the control signals. The other set of signals which originate from the data and go to the control are called the status signals. Primarily the role of control signals is that to perform an operation or a set of operations, you have to generate the control in a sequence. That is, you have to generate a sequence of inputs to the data part to be able to perform. For example, if you have to latch the data into a register, you have to generate the load signal. If you have to clear a counter, you have to generate the clear signal. If you have to select a certain input to the multiplexer, you have to generate the proper select signal with the proper value. If there are 4 inputs, then it is a 2-bit input which will select which input should be selected. So all these signals are coming from the control part and going to the data. Whenever you want to change the flow of control signals, when the control signals will follow a certain flow, but when you want to change that sequence, then there is some status information which comes from the data part which goes to the control signal. So these are typically things like output of the comparator. This could be a decoded value of a counter output. Basically when you are taking an action, so typically when you look at it, this corresponds to, in a very high level description of your application, this corresponds to if then else, condition evaluation for if then else, condition evaluation for while or repeat. Whenever you have such constructs in your description, the algorithm that you want to implement on the hardware, then those have to be translated into appropriate change in the sequence of control signals, because after all you will follow a certain path if the condition for if is true or condition for if is false, and those things will appear as the status signals. So the role of control is, so role of the data part is to actually perform the data transformations. It contains the storage units, registers, memories and so on. It also contains the data transformers like ALUs, and the role of the control is to generate the appropriate sequence of control signals so that you are able to map the particular task or particular algorithm onto your data part. Now how do we generate this set of control signals? This is what we are now considering, and we already have looked at 2 options for it, and today we will look at the third option, but let's review what are the options that we have. When you want to design a control unit, primarily this for simple systems we are talking about. So if it is a very complex system, you already done a partitioning, identified the subsystems, and you can again follow for each of the subsystems, you can follow one of these approaches as far as the design of the control part is concerned. What are the approaches? You can follow an ad hoc approach. Now many times when it is a very simple problem, you can select a combination of MSI and SSI modules. What we mean is you can select a combination of decoders, counters, registers, SSI or gates. You can design, silence please, you can select a set of such modules, interconnect them and implement the design that you want to have. So you may have some notion of a state machine or some notion of what type of a control sequence is required, and you can generate using these. So there is of course what is called a random logic implementation. Random logic implementation is again basically using SSI modules, using gates, but their starting point could be a state machine description. You can start from draw a state machine, identify the states and identify the implementation mechanism for the states, flip-flops or counters. Then for each of the transitions that you have in your state machine, you can implement the logic required to implement the transition, or you follow either a Mealy approach or the Moore approach, design the state register and write down the equations for the combinational logic in terms of input-output relationship. Then you follow some type of a gate implementation for doing that. So this type of an approach is called random logic implementation. Today what we are going to consider is the third approach, which is called the microprogrammed control. Microprogrammed control can start from either from a state machine description, but here we will talk of a modified state machine description. We will say what these modifications are, or we could also start from an RTL description. It's an algorithmic description, but it is RTL in the sense that your data path is already reflected in your description. That is, you already have your storage allocated, you already have your functional units, ALUs. So you are already done this mapping. So you can specifically say that if I want to perform a certain transformation, how can I perform that transformation? What multiplexers have to be selected? What input has to be given to the ALU to perform an addition operation? Those things are already known, and then you generate using a microprogrammed control. Of course, this RTL description thing will get more clearer as we proceed beyond this, let's say module, when you go to the next module, but for the present we will concentrate on, so you can relate to what we have done with the state machine, that how will we do for the microprogrammed control. So first let's introduce the terminology. We will come across number of words in the context of microprogrammed system design or microprogrammed control design, and we will talk about that. So first thing is a microprogram. First of all, why the name microprogram itself? Okay, so the name microprogram essentially comes from micro is not really small, it comes from lower level. Okay, so basically here the micro essentially, so you talk in terms of, when you talk in terms of programming, you have a high level program, whichever Pascal, C, Fortran, any language that you use. Then you have an assembly level program. You all have studied some computer architecture and you know what assembly level is. And assembly level and equivalent machine level. Assembly level and machine level are typically at the same level of abstraction, except that assembly level gives you some ease of programming. Then it is below that, and that's why it's called a microprogram. This programming is at a level even below the machine level. So it is internal to the machine typically. Typically a user can program a machine or program a processor in assembly level or machine level. But this is, for example, if you really consider a processor design, of course, we are not always talking of processor designs. We are many times talking of designing digital systems for specific applications, which will directly in hardware implement the application. But if you, let's say, talk of a processor, then each instruction will go through, there will be a program for implementing each of the instructions, and that's the microprogram level. That's a level at which the units, the parts of the components of the machine work, and this is called the microprogram. Microinstruction are the components of the microprogram. Each instruction of a microprogram is a microinstruction. So it is typically so this is, all these are, again microprogram you can write it as 1-0 at binary, and there are also methods available, there are also systems available where you can write it in a symbolic notation. But then the levels are not different, just like you can write either in machine level or assembly level. There is a 1-to-1 mapping between an assembly level instruction and a machine level instruction. Similarly, there can be a 1-to-1 mapping between a symbolic microprogram and a binary microprogram. Many times we tend to directly write in binary when it comes to microprogram, but that's not necessary. One can develop a mnemonics, one can develop a set of symbols, and you can write it in the symbolic form. Again, microinstruction you can write it either in symbolic or you can write it in binary, but microinstruction corresponds to one instruction of the microprogram. Micro operations, every microinstruction consists of a set of micro operations. These are the basic indivisible operations of your hardware design. That is, each particular something which you cannot really divide. For example, if you want to transfer data from one register to another register, it's a micro operation. If you have to perform an addition and store the result into the accumulator, it's a micro operation. There is nothing that is smaller than that you can do. So that is, those are indivisible parts, and those are called the micro operations. Typically the hierarchy is a micro instruction consists of a set of micro operations, and a microprogram consists of a set of micro instructions. So this is the hierarchy as far as. So now next we come to the Microinstruction format. So you have to decide, so microinstruction typically consists of a large number of bits. Each microinstruction may have starting from something like 20-25 bits up to even 200-240 bits are present in a micro instruction, and how the format essentially defines that what bits perform which micro operations. You have to define the functionality of each of the bits, and those represent that information is called the micro instruction format. As we go ahead, we will come to this. Microsequencer is a very key component of the microprogrammed control, and the role of a microsequencer is to control the sequence of micro instructions that are generated. Typically, as we will see in the next diagram, that it is called the next address generator. You have generated an address which corresponds to the present micro instruction. We have to generate an address corresponding to the next micro instruction, and that's called the microsequencer. So it's sort of a heart of the design which does the sequencing of the control unit. Control or microprogram ROM, after all, the sequence of control signals that are required to be generated are stored somewhere, because we are talking of a design of a hardware unit. Once this particular thing is designed, it will function exactly each time. For example, let's say I am designing a processor, so you are not changing the instruction set each time. The instruction set is fixed. We are only going to give a sequence of instructions, but the instruction set is fixed. So this basically is going to decide how this instruction is decoded and executed in the hardware. So that all that information, the set of control signals that are required, of course this information is stored obviously in a binary format, and that is stored in a control ROM. Micro instruction register, there is an internal component, and this is required as an interface between the control and the data, and we will see that in a moment. So these are the various terms that we will come across, but let us first look at the design of the block diagram of a microprogrammed control unit. What we generally call it as a control unit, this is the control unit. And this is the data unit. I have not gone into the details of the data unit. The advantage of this type of a design approach primarily is the control unit is structured. I typically have three components. I structured in this manner. I have a sequencer, I have a control ROM, I have a register. Output of the sequencer goes as an input to the control ROM. Output of the control ROM goes as an input to the register. Output of the register is split. One set goes to the data, another set goes back to the sequence. So these are the three main components over here. We will see that there could be smaller components as well, and I am not going into the details of the data part, but now let us look at, if you remember, the partition that we have. Let us relate it to this partition. Here we considered this as a black box. Here now we are going into the details of this. So here the status and control signals. So if you relate it over here, so these are the control signals, and these are the status signals. What is coming from the data part and going here is the status signal. What is coming from the control unit to this. Okay, let us look at, so as I said before, the role of the sequencer is also called the next address generator. Because the primary function of the sequencer is to generate the next address. The next address is, after all, what is this input? This input is the address input. This is the address input, because ROM has only one input, address input, of course apart from the chip select and so on. So those we are not considering here. It has an address input and it has an output which is the contents of that. The contents of a particular address are nothing but the control signals, and the sequencing you do by controlling what address I am going to generate. If you consider a particular, so each of these, this corresponds to a micro instruction. At each control step or each clock cycle I will generate a micro instruction. This micro instruction will get stored in this register, and this is called the micro instruction register. micro instruction register, and this control ROM is also called microprogram ROM or control ROM. Both of the things are used, and basically this contains the set of control signals. So we will come to, first of all, why we use such a design technique. We will see that, but we will also look at all of them. I have shown to be, they are not 1 bit wide, but they are multi-bit wide. That's why they are shown with double lines, and we will see that what is the width of these and how do we relate to it. But a very important thing to realize is this structure is an extremely flexible structure, in the sense that if I want to change a set of control signals, the only thing I need to change is the control ROM. And also, even to look in terms of a design, when I want to implement a subsystem, I can, because I am breaking it neatly down into 3 parts, the sequencer part, the control ROM, and of course the register is nothing but it's of course clocked, and this just stores the next micro instruction. So what is the role of this register? Because control ROM we have seen, sequencer we have seen, data part we have seen. The role of this register is essentially, I cannot have, so this is a synchronous design. Okay, we are talking of implementing a synchronous design. It's not an asynchronous design, and you cannot have any loops of combination logic. The role of the register is, I perform an access of the next micro instruction, and during all this time the present micro instruction is stored over here, and that's what is being used by the data part. This micro instruction is being used by the data part to is executing that. We will also talk about what the timing that is involved in it. So these are some simple advantages and disadvantages of using a microprogrammed control. So one has to make a choice which type of control. We talked of 3 options, and one has to make a choice which type of control one should use. A flexible and structured design, we already have looked at it. The structure comes because of the fact that control doesn't change. Say, for example, if you look at the state machine implementation, there is really no structure. You can directly, if you are using a random logic, you can actually use number of flip-flops, different type of encoding, different type of gates, and if you draw the schematic diagram of it, if you draw the logic diagram of it, the structure will, from one design to another, it will look completely different. Whereas here, this particular subdivision into blocks is more or less fixed. So that's the structure part of it. The flexible part of it is, when you are developing a design, there will be a need to make some small changes in your state machine. You introduce additional states, change the signals associated with the states. If you try to do these things in your random logic implementation, you might have to go back and redesign completely. Just change of one particular state may mean everything has to be redesigned. Whole logic might have to be redesigned. So imagine if you have already wired it up, or if or if you have actually done a VLSI design of it, the component has been designed, and if you really want to make another change, do all the simulation and so on, it's going to be extremely time consuming and expensive. Whereas in this situation, I may need to only change the ROM, contents of the ROM. Many changes can be accommodated by changing the contents of the ROM, but sometimes we will see that the others may require a little bit more change. This is another consideration. Testing sequences can be easily incorporated. Many times how the system will be tested is looked at after you have done your system design. Of course, we will say that it's not always a good practice to do this. You should think of how the testing should be done right at the time when you are doing the design, but practically many times the way it works is you do the system design and then you look at how testing has to be done. So testing may also involve some circuitry. Testing may not be possible to be done exactly in the same manner as the way the design is working. In case of microprogrammed control design, it may only include that I may have to program a few more instructions or in the control ROM, by which I can excite the paths, I can actually activate the paths which are required for performing the testing, and I can get my testing done. Whereas in a random logic design, it may involve redesigning completely different circuits, or if you want to make it optimal with the existing circuits, you might have to redesign the existing designs also. Easy to document and debug, and this essentially comes from the way the software works. It's easy to, because microprogram is written in a similar manner as you write a program, especially if you adopt symbolic microprogramming, where you write the symbolic microprogram and you have what's called a microassembler. Microassembler is nothing but a lookup table which takes the each symbol and generates its equivalent machine binary code, just like your assembler does. So if you work with a symbolic microprogramming language and a symbolic microassembler, you can do very easy documentation and also debugging of that. Changes are easy to reflect and so on. But then it's not always one adopts microprogrammed control, and the reason why one doesn't always adopt is these two. When it comes to small systems, it's very clear that microprogramming is more expensive. When it comes to larger systems, it can go either way. Microprogramming could be more expensive, or sometimes it could be cheaper also. Because there is an additional ROM involved, there is sequencer involved, all of that is actually gets integrated in a random logic design. Here they are all separate. ROMs are very cheap if you talk of large sizes, because again, because of the structure design, the component can be very compact. But when you talk of small ROMs, they are not very cheap. They could be more expensive. So the other major disadvantage is this is definitely slower than random logic. We will see that why it is slower. So microprogramming is still used when you want a flexible and structured design. Another reason it is used is when you are doing prototyping, many times people use the microprogramming because you are in the development stage. A lot of changes are going to come in the control, in the protocol, in the interfaces. So you go ahead and do a microprogram design. At the end, when everything is frozen, once you are very satisfied with the design and it's going to go into production, you reduce the cost and the size and this increase the performance speed by translating this such a microprogram design into a random logic design. So sometimes a two-stage process is also followed. Now let's look into what constitutes the microinstruction format. There are four very distinct parts of a microinstruction format. These are all typical. There may be specific situations when one or more of them may be absent, but these are what we are talking of is a very typical microprogrammed control design. So the whole thing is called the word length, and let's say this is the number of bits that we have is W. There are four parts of it. The first part is the data part control signals, and let me call it M is the number of control signals that are there. We will later on see that how this M can be reduced, or what are the implications, and we will see that later. But presently, as far as the interface is concerned, we take it that there are M bits. Sequencer control, we require some bits for controlling the activity of the action of the sequencer itself. The sequencer also can be a very simple thing. It could just be simply be a counter, or it could be fairly complex, and one may need to have some bits to control it, and there are k bits to control the sequence itself. I will come back to the status control select. There are S bits to select what the status is, and I will consider this in a little bit more detail. Next address, I need to perform certain type of jumps. Anytime you have conditionals or iterative loops and so on and so forth, there are jumps involved, and I need to generate the next address, and there are bits reserved for next address. So these things will get clarified once I discuss the structure again, but let us now look at it. What is happening over here? The total width of this microinstruction format is nothing but M plus K plus S plus N. All these four together, they constitute the microinstruction format. Within this, there will be, of course, be fields. These do not just define the complete format, they are only defining in a broad way. So then you have to go down and consider what each of these bits are going to do. Within the data path, there are number of bits, M bits, how these bits are controlling the data units. Similarly, you have to consider that sequencer control, what action the sequencer takes under each of the encodings for the sequencer control. Let us say if this is 3 bits, that means it could be 000, 001, 010, and there could be different actions be associated with these encodings. Same thing is true in case of other. So now let us look at the sizes of the components. We have already, when we considered this, we had the 4 blocks here. We will of course now increase the block by 1, and we will see that how that block comes. But let me first consider what the sizes are. If you just look at the data part, these are M control inputs and S status outputs. So I have, so this is as far as the interface of the data, as we said there are control inputs and there are status outputs. These are different from the primary inputs and primary outputs. There could be more primary inputs and more primary outputs which do not go to the control. After all, this particular system, so when you consider what we are talking of is, there are two components inside. This is your system, but this particular system has some inputs and outputs. These are called the primary inputs and these are the primary outputs. I am only now bothered about this control and data interface that is present. This is data, let us say this is control, then these are the control signals and these are the status signals. So I am only bothered about this. Apart from this, typically the primary inputs and primary outputs can all be considered to be going to the data part, so I am not talking about that, I am right now only talking about. So there are M control inputs and S status outputs. Some of these status inputs could be primary inputs. For example, if you consider the design of the GCD, we had a signal called start. So this particular start signal, if you remember the GCD design, so it was part of the state machine, and initially at the initial state I had to check whether start is high or low and then perform a state transition. So that such a signal, because it is controlling the flow, it is actually also a status signal. So the implication is a signal like this, which is a primary input, will be part of the status that goes into the data part. So this will also contribute to S, the status signals that are going to the control part from the data part. When you consider the microsequencer, we will consider this k plus 1 inputs and n outputs. We can consider it in two manners. Either we can say that all the status inputs are going to the microsequencer, or we can say that at any given point in time we are only looking at one status signal. So there are k inputs which are coming from the microinstruction format plus one input that is coming from the status. We will see this in relation to the status multiplexer in the next diagram. And there are n outputs. These n outputs correspond to the next address, and these are the n outputs. Status multiplexer, we have another component which selects which status I am considering. So as status inputs, S select lines. Here S is greater than equal to log 2 S. That is the assumption that we are making, that between the small s and the capital S, I am always consider the small s is to be greater than equal to log 2 of the capital S. So I need S select lines for the multiplexer to select one of the S status inputs and one output. And when we consider the control ROM, I have n address lines are going to select, so n is again greater than equal to the n micro instructions that are stored, and these micro instructions have to be addressed by address lines, and there are n bits. So the ROM size itself is n into w, w is the width of this, and the micro instruction register is w bits wide. These things will get cleared. I will spend a little more time talking about this using the next block diagram, because now we made one change in the block diagram. We have introduced one more component, which is the multiplexer. Let us look at this diagram. So one change that I have made is I have introduced a multiplexer and used a select line. Sometimes one considers this multiplexer to be part of the sequencer, sometimes one considers it outside. It is up to us. Presently we are considering it outside. All this is again the control part. The S status lines that are coming, and at any given time I am only selecting one of these status lines to go and perform a check. We will see that what is the implication of this, because this has a implication in terms of what modifications you need to do into the state machine. So if I now look at this register output, I have some bits going into the sequencer. I have selecting this multiplexer input. I have to select which of the status I am going to consider in this particular control step, and that is being selected using this as select line. So, the one of these lines will be selected. Remember, this has the width of 1, rest of them are all buses. The sequencer control is going over here. Okay, one more thing I should have shown. This is the next address. If I need to select the next address, this also has to go over here, that is n. This makes it m plus n plus k plus s that I showed as the width of this. So, this is the width, this is all the bits coming. This register does not do anything but just latch this and puts it over here with every clock. The width of the control ROM, it is clear that n bits are address lines, so it is n into w. I am using n lines to address capital N locations. So, the relationship I already shown that n is greater than equal to log 2 of n. This S lines, again S is greater than equal to log 2 of S. It is going to select one of the status lines, and the role of the sequencer is to either to pass this on or to generate some other address. We will consider the sequencer design in greater detail in the next class. But the sequencer design is the one which, macro sequencer is the one which generates the next address. This is the next address.
So what sort of K is this K coming from register?
K, the K is the controls the sequencer action. It controls, it's sort of an instruction for the sequencer itself. The sequencer is capable of performing, choosing between some of the options it has for generating the next address. The role of this K will become clearer again when we look at the design of the sequencer. For the present, you can assume that K is an inputter sequencer and defines the role of the sequencer in this clock cycle. The sequencer itself has certain capabilities and it defines the sequencer. I am using the word sequencer as a microsequencer. I am not writing it here microsequencer, but basically this is a microsequencer. Okay, so now what we have over here is, so you can see that W is nothing but sum of all these. This is the width and this is the W as the input. N is the input, which is the number of address lines over here. And let us look at what is the role of this multiplexer in selecting this status lines and putting here. If you remember your state machine, let us look at some. Let us say if you consider under some input condition, let us say there are 2-bit input, 0 0 I go over here, 0 1 I go over here, 1 cross I go over here. This is, let us say, some part of the state machine. I am looking at 2 bits of the input and doing a 3-way branch. If I now want to translate this in my microprogram, I am going to associate, let us say it is a Moore machine, the control is a Moore machine. I am associating some control signals here, some control signals with these, some control signals with each of the states. What is the implication over here? The implication is, I am going to look at 2 bits of the control signal and either generate this set of control signals, this set of control signals, or this set of control signals, depending upon what these 2 bits are. But what is going to happen in terms of this implementation is, these control signals that you need to generate over here corresponds to some micro instruction. They are going to be stored as part of, see, these control signals are a 1-0 pattern. Basically with each we have to associate some 1-0 pattern, and this 1-0 pattern is nothing but a micro instruction. So now I had to be able to select, looking at 2 inputs, I had to be able to select between 3 sets of micro instructions. Implication is, this sequencer should generate one of these 3 addresses, so that I can go to the corresponding micro instruction which stores the control signals of either this. So let us say this is some state S3, this is S4, this is S5, this is S6. I let us say map this. I map S3 to address 3, S4 to address 4 of micro instruction S5 to of microprogram S5. But in this particular model, I do not permit this direct implementation of such a state machine, because the problem over here is like this. The problem is, I need to select between 3 of the micro instructions. That means typically what happens is that when we will see the sequencer, the next one can be generated automatically. The sequencer has a capability of jumping to the next one. But I need to also have 2 more addresses coming, and I have to choose between one of the 3. So instead of doing that, I always choose, typically, of course, one can also design a Microprogrammed control in this manner, but typically we choose 1 out of 2. The implication is I will translate this state machine into a 2-way branch. I can look at only the first bit over here. One cross, 0 cross, and now I can look at the second bit over here. So now this is corresponds to my S3. This is some other state, and this is actually, this I will travel when it is S4. This is equivalent of that, this is equivalent of this, and this is equivalent of S3. There is some S3 dash, let us say, some new state. So I can transform this into this manner, and advantage of doing this is now I am doing just a 2-way branching. So I can make it that I always either go to the next state or I go to some arbitrary state. The advantage of this is I need to supply only one address over here, which is the conditional jump address, and I need to only select one status signal. Now the status signal that is selected in this particular state will correspond to this input. The status signal that is selected in this particular state will correspond to this input, second input, and I can write it as a 2-way branch. So doing this type of an implementation in state machine is not a problem at all. But doing this type of an implementation in Microprogrammed control can be very expensive, and we will see the reason for this. Primarily you have to store more than one address in each micro instruction, and that will mean that the size of the micro instruction will keep on growing. And if it is not very often that I need a 3-way branch, which will be mostly I will only need 2-way branches or no branches, then all those bits that are reserved for the next address will all go waste, and that is the reason that one typically tries to do it in this manner. So what happens over here is you store this and you select the status signal that you want to check, and the sequencer will proceed and look at this particular status signal that you have selected over here and make a decision whether this particular status is true or false, and accordingly either go to the next micro instruction or jump to another micro instruction. And this action is done by the sequencer. Yeah. This end?
No, so the other one from the next address.
This is the next address. This is the address that is being generated by the sequencer. This value may either correspond to this, or this value may correspond to, for example, if you look at this particular status, it may either correspond to this or this. So this decision is being done by the sequencer, because I need to generate a separate set of control signals if this is true, and I have to generate a different set of control signals if this is false. And this decision is being taken by the sequencer. The role of the sequencer is generating the next address. So if you consider your state machine, the role of the sequencer is to generate the transitions. So wherever you are making a transition, you need to generate that. So now let us look at the clock period computation part of it. We follow exactly the same approach as we have done in case of the state machine when we are doing the clock period. So I define again some terms. TDP is the maximum delay in data part. When we say maximum delay in data part, what do we mean? Maximum delay in data part essentially corresponds to, if you consider any 2 storage locations, what is the combination logic delay between those 2 storage locations? I am assuming my whole system is clocked by a single clock. All latching of all the registers are taking place at the same rising edge. So the delay of the combination logic between any 2 storage elements, if you consider such a maximum delay, that is the delay of the data part. The status register, maximum delay for status generation. So if you consider this data part, this part is, let us say this is my data part. If this is a register, and this is some combination logic. then this is, of course there may be many such registers and many such combination logic, but whatever is the maximum of such delays defines the TDP. But T status register is, I am generating my status output, this is my status output which is going to the control, and is based on again some inputs coming from registers, it could also be based on some primary inputs coming. So the maximum delay of this is I refer to as T status. Typically TDP will be greater than equal to T status. Okay, because this is also a path, but this is the maximum of all the paths which are not even involved in doing the status generation. There could be paths which are do not control. Typically, for example, the status comes from things like comparator output, things like some decoder and so on, which are going to generate the status. So this is the maximum delay for status generation. Status multiplexer is the delay of the status multiplexer. T sequence is the microsequencer delay, and T ROM is the control ROM delay. T register is the register delay. This also includes the setup time. So typically we have been talking of two different delays, so but here I am including the setup time, and I am talking of T setup plus T register delay, delay of the register to be T register. So these are the various components, and now it is fairly easy to see that what is the clock period, how do we define the clock period. Now if you consider this overall system, so I already have data path characterized. So I have this TDP which is associated and T status that is associated with this. So now, of course TDP is a register paths, the delay paths from one register to another. Now if you consider this particular system, there is also a path over here. The path is this is the path. So this particular is T status plus T status multiplexer plus T sequencer plus T control ROM plus T register. This is the path, and between the two clocks, so you have these clocks, between the two clocks what you generated, the micro instruction that you have generated now, and so after all the micro instruction that you have generated now is going to affect the next micro instruction through the sequencer. So but it may also affect the status, because if you have some comparator acting on output of some register which you have just latched, that comparator output may change. So that will be the T status. So T status plus T status multiplexer plus T sequencer plus T control ROM plus T register. The clock period should be more than this. And that is what is being reflected in this equation. TDP and T status are associated with the data path. By analysis of the data path, you have to get these two values. So now, the way for the moment I am assuming my sequencer logic is a purely combinational logic. In the next class when we design the sequencer, we will find that there could be also be loops within the sequencer. What we call as loops here is, basically as far as the delays or computation is concerned, the clock period computation is concerned, we have to consider all paths which go from one register to another register. A register output to register input. It could also be the same register input, that is also a loop. So anything which goes from a register output to register input is a path, and the clock period has to be maximum of all such paths, because once you generate a register output, it should be stable at the register input for latching it in the next clock in a single clock design. So TDP was one such thing which was coming from the data path, and the loop that I have just now considered results in the next component of it, T status plus T status multiplexer plus T sequencer plus T ROM plus T register, and my clock period should be more than either of these two. It should be greater than the maximum of these two. From this equation, of course it looks like that I have various components, so this seems to be larger, but that is not always true. It all depends upon your design. Remember, TDP can contain components which have a lot of delays. For example, you could have a multiplier, and this multiplier, a combinational multiplier, 32 by 32 bit combinational multiplier could be a fairly large delay. So it may happen that actually it is the TDP which dominates this and not this, but there are also situations when this can dominate. So you have to be clear that if when you are doing a design, and the reason, one of the reasons that the microprogrammed control is considered to be a slow implementation is TROM. The TROM is for larger designs, the ROM delays could be significant, and this part is in a random logic design we don't have any ROM there. So it is only implemented as some logic design, and that can be much smaller than the TROM that we have, the delay of the ROM that we have. So this is a fairly significant contributor to this delay, and because of this sometimes the clock actually depends upon this component, which makes it that your clock period is going to be larger.
So this T status may depend on TDP.
T status and TDP are, let's say, two characterizations that delay characterization we need of the data path. They may be equal, they may be different, but TDP will be definitely be larger than T status.
T status may depend on this TDP.
No, depend means what? It depends upon, both of them depend on the data path. They may be, TDP may be same as T status, or TDP may be greater than equal to T status. Depends upon, see what is a T status? Please, you have, when we have considered this, we are saying that from the data part, we have some status signals that are getting generated. What are the components of the data part which are contributing to the status signal generation? For example, there may be a comparator here. Input of this may be two registers, R1 and R2, and this comparator output may be going over here. Now what happens? Load of this comes from, load enable comes from the control for this register. So this particular, now delay of this comparator is one T status, because after the load signal comes, whenever the load signal comes, the register value may change, register will have some inputs and I will load a value, and after that value comes, the status output will change, because depending upon what the value in R1 is and what the value in R2 is, I may get a greater than or less than output, but I will not get it immediately, I will get after a delay which corresponds to the comparator delay. So this could be one source for generating the status, but there may be many comparators, there may be other decoders and so on, so you have to consider the maximum of all such delays, and that is T status. Now as far as the TDP is concerned, I could have these two register outputs could be going to a multiplier and going to another register. This also has a load enable. So within a clock period, after I have given the load, and I can give the load enable for this in the next clock, within that this output should be stable. So this may be determining my TDP. So this multiplier may not be participating in generating the status at all. Okay. So typically that's why I said the TDP will be greater than equal to T status. That will be the typical situation. Of course one can create other situations also. So now that gives us the clock period. We will actually improve upon it when we consider the design details of the sequencer. Here I have just abstracted the sequencer as a combination logic, and I said T sequence is the delay of the sequencer. But when you really consider the performance, there are two components to this performance. Performance does not just come from the clock period, but performance comes from T clock into N clock, the number of clocks. Remember, when we did the splitting of this state machine, we have also in turn increased the N clocks, number of clocks, because all transitions are going to take one clock. Here I could do a three-way decision, but let's say if I am going in this particular path, here I would have gone in one clock, here I am taking two clocks to go. So I have also in turn affected the number of clocks. So there is also one disadvantage of doing the microprogram. So they affect both these, they affect both T clock as well as N clock, typically increases when over the random logic implementation of the state machine, and that's why the total time which is nothing but T clock into N clock, has a tendency to go up. Later we will consider methods of improving it. A very simple method of improving which one can think of is, let us say if this is the part which is dominating, what one can do is one can put a register somewhere in between. This is a weak path that you are having. I can put there are solutions and people use such designs and they are very attractive alternatives. You can put a register here, you can put a register here, or you can put a register at both places. And these techniques are called pipelining techniques. What happens is once you put a register, this path gets broken. My definition of my clock period will be maximum of this path, maximum of this path, and maximum of this path. I have split my path into 3 parts and I have to take the maximum, so I don't have to add this. Of course small register delays will get added up in each of the paths, but still it is much less than. So you can split it into 2 or 3 parts. One can use both registers, one can use one register. We will discuss this, but please remember that introducing registers may help you in reducing T clock, but also has an effect of increasing number of clocks. Because the status that you generate in this particular clock period is not going to be visible for either one more clock period or 2 more clock periods. So you may not be able to do an immediate branch, but you may have to go through some set of states before doing that. So this is also not a solution which, so you have to actually optimize the performance, that how many stages of pipelining you should use, whether you should put 1 register or 2 registers or 3 registers, because that has also an effect on increasing the. So what you may gain by reducing T clock, you may sometimes lose by increasing the number of clocks. But this is something fundamental to all sequential circuit designs, synchronous sequential circuit design, that T clock into N clock is a total time and you have to bother about both of these when you are talking of performance. We will stop over here and